We are now on the second page of your notes, and we're going to be talking about simple machines. Machines are things that make work easier to do by changing the size of the force, the direction of the force, or the distance over which a force acts. There are 6 basic simple machines. Every other machine is made from these 6. For example, a fan would be made of a combination of these simple machines. So the first one is a lever. A lever is like a seesaw. It pivots back and forth on a fulcrum, which is the point where the pivoting happens. A wheel and axle is a second type of machine. In fact, a screwdriver is actually a type of wheel and axle. This narrow part here is like the axle, and this wider part is like the wheel. And it is important for the handle of the screwdriver to be larger than the stem, because that gives you more force as you turn the screwdriver. If you just use the screwdriver like this, it wouldn't do you very much good. Next is a pulley, where a rope goes over a spinning wheel. An inclined plane is a ramp. A wedge is 2 ramps put back to back. For example, a knife is a wedge, or a log-splitting wedge is a wedge. A zipper, go figure, is also a wedge. A screw is a ramp wrapped around a central stem. Out of these 6 machines, 4 are actually types of the other 2. For example, a pulley and a wheel and axle are just types of levers, and a screw and a wedge are types of inclined planes. So let's say you're walking up a ramp. Why does that make your work easier? Well, if you have to step upwards in one big giant step, that's going to take a lot of effort and a lot of force. Versus if you go slowly up, you can put a little bit of force out at a time and spread it over a much longer distance. And that way you never have to exert a big amount of force. You just exert little bits of force over a long distance. And that's how most machines work. There's a trade-off between the force and the distance. Now, the work you put into a machine is always equal to the work you get out of the machine. In a perfect world with no friction, those are perfectly equal. But in real life, you have to do a little extra work to overcome the friction. So the work you put into a machine must not only produce the work output, but must also overcome the friction of the machine. So the work you put in is still equal to the work you put out, it's just part of the work put out goes to overcome friction. This formula helps you understand the trade-off between force and distance. The work input is equal to the work output. So the force times the distance that you put in must equal the force times distance that you get out. So if you put in a greater distance, like walking up that long ramp, you can also put in less force. You'll get out the same effect as if you had put in a huge force and a much shorter distance. And that's the trade-off. Either a long distance and a little force, or a short distance and a greater force. So a machine works by changing the force, the distance, or possibly the direction. For example, a pulley. When you pull down on one side of the rope, the other side of the rope goes up. So that pulley changes the direction of your force. Or if you have a seesaw, you push down on this side of the seesaw and this end goes up. Push up and this side goes down. So that changes the direction of your force. In real life, all machines have friction. Therefore, no machine is ever 100% efficient. A simple thing like a lever has only a little bit of friction right here where it pivots, so that would be maybe 99% efficient. But if you have a car engine with all of the gears and the motion and the scraping against each other, a car engine may be only 30% efficient, just because of all the friction that is exerted. Now let's look a little more closely at the 3 classes of levers. There's first class, second class, and third class. Here's a quick way to remember which type of lever is which. Free, F-R-E, like free, F-R-E-E, without the last E. And that stands for fulcrum, resistance, effort. F-R-E. So the fulcrum is in the middle on a first-class lever. The fulcrum is the place where the pivot occurs. So for example, a seesaw is a first-class lever because it pivots in the middle and then the two ends of the levers are on the sides. You put in the input force, so your hand puts in the force, and then the output force is on the other end. The tip of this screwdriver lifting up the paint lid would be the output force. With a second-class lever, resistance is in the middle. The resistance is the load. So, for example, a wheelbarrow would be a second-class lever. The wheel is the fulcrum, where the wheelbarrow pivots as you lift it. The load goes in the middle, and your hands go at the end of the handles, and that's your input. So you put in a force and lift the load in the middle. For a third-class lever, the effort force is in the middle. So, an example is a broom. Your effort is here in the middle. This hand just lets the broom pivot and swing back and forth. And your output is here at the end of the broom where the brush part is. And that's how a third-class lever works. Let's take a look at several different levers and see what type each one is. First, let's look at a pair of tongs. You'll notice the fulcrum is in the middle. This is where the pivoting occurs. Your input force is where your hand reaches, and the output is where you would grip. Since the fulcrum is in the middle, F-R-E, it's a first-class lever. Here's another type of tong. This time, your effort is here where my fingers are. The pivoting happens here, so this is your fulcrum, and the output is right here. So, since your effort is in the middle, F-R-E, E is a third-class lever. Here's a pair of tweezers. Your effort is in the middle, the fulcrum is here, and the output is here. F-R-E, third-class lever. What if this was a pair of nutcrackers, like you would crack pecans with? You would place a pecan in here, and you would press here to crack the nut. So your effort is here, the fulcrum is here, and the pecan, the load, or the resistance, is here. The resistance is the middle, F-R-E. It is a second-class lever. Finally, let's look at a pair of scissors. Here's your effort, where my hands are. There's the fulcrum. There's your output. What kind of lever has fulcrum in the middle? That's right, a first-class lever. Let's pretend that this is a door. It's actually a little phone or computer stand. But this is the fulcrum, where the door opens and closes. That's where the hinges would be. This is where the handle would be. So here is your effort. And what about the load? Well, if you took the mass of the entire door, the center of mass is here. So your load or your resistance is in the middle. So effort here, pivot or fulcrum here, and the load averages to the middle. If your resistance is in the middle, F-R-E, then that must be a second-class lever. Who would think a door is a lever? But it is. So examples of first-class levers include a seesaw, scissors, and a certain type of tongs that look like scissors. A second-class lever has the output force in the middle, which is the load or the resistance. And examples include a wheelbarrow and a nutcracker and a door. For a third-class lever, the input force, the effort, is in the middle. You put in the effort. An example of a third-class lever would be a broom, a bat, a golf club, an oar, a hockey stick, tweezers, or tongs that look like this, pinching-style tongs. Finally, let's talk about the difference between ideal mechanical advantage and actual mechanical advantage. Ideal mechanical advantage is if you had an ideal world with no friction. If you had no friction, then you would get out the perfect, full 100% advantage of the machine. If there was no friction, you could put in work and you would get out exactly the same amount of work with no effort lost to friction. So the number of times a machine multiplies your work is the ideal mechanical advantage. For example, if a lever had an ideal mechanical advantage of 2, that means it's twice as easy to lift the object using the lever as it is to just lift it with your hands. If you have a lever with a mechanical advantage of 5, it's 5 times easier to use the lever than it is to lift the object. If you have an advantage of 0.5, it's half as easy to lift. In other words, it's actually harder to lift. So why would you ever want to use a lever that had a half of a mechanical advantage? It's twice as hard to lift. For example, a traffic arm at a parking lot is a third-class lever. Here's where the pivot is. Here's the effort, and there's the load. It's not good if you lift the load in the middle. That actually means you get less force out. But the advantage is you have very little distance. You move that far. The output arm moves that far. So that's the advantage. You put in more force, but you put in less distance. You got out a greater distance, even though you got less force in the end. Actual mechanical advantage is the real advantage of a machine, taking into account that some of your effort is lost to friction. So the actual mechanical advantage is either equal to the ideal or, more likely, slightly less. The AMA can also be greatly less than the IMA if there's a lot of friction in the machine.